If you've ever wondered what computer science students actually study at top-ranked universities, the answer might surprise you. While every university has its own curriculum, the core courses are remarkably similar. In this video, we'll walk through the essential CS courses you will find at the world's top-ranked universities and explain why each one matters. Introduction to Programming. Every computer science journey begins here. You'll learn how to write code, solve problems, and think like a programmer using languages such as Python, Java, or C++. From variables and loops to functions and debugging, this course teaches the fundamental skills that every software developer needs before moving on to more advanced topics. Object-oriented programming. Once you know the basics, it's time to write larger, more organized programs. Object-oriented programming introduces concepts like classes, objects, inheritance, and polymorphism. These ideas make software easier to build, maintain, and expand, and they are used extensively in modern application development. Data structures. How do companies like Google search billions of web pages so quickly? The answer starts with data structures. You'll study arrays, linked lists, stacks, queues, trees, graphs, and hash tables. Choosing the right data structure can dramatically improve the speed and efficiency of your programs. Algorithms. Data structures store information, but algorithms tell computers what to do with it. In this course, you'll learn sorting, searching, recursion, graph algorithms, and dynamic programming while analyzing efficiency using Big O notation. It's one of the most important courses in every CS degree. Computer organization. Have you ever wondered what happens when you press a key on your keyboard? Computer organization explores how processors, memory, registers, and assembly language work together. Understanding hardware helps programmers write faster and more efficient software. Operating systems. Operating systems manage everything your computer does. This course explains processes, threads, memory management, scheduling, synchronization, and file systems. You'll discover how Windows, Linux, and Mac OS coordinate hardware and software behind the scenes. Discrete mathematics. Unlike calculus, discrete mathematics focuses on logic and structures that computers use every day. You'll learn proofs, sets, relations, graphs, combinatorics, and Boolean logic. This mathematical foundation is essential for algorithms, cryptography, and theoretical computer science. Linear algebra. Artificial intelligence wouldn't exist without linear algebra. This course covers vectors, matrices, matrix multiplication, eigenvalues, and eigenvectors. These concepts power machine learning, computer graphics, robotics, and data science. Calculus. Calculus teaches how quantities change over time. Students study derivatives, integrals, optimization, and multivariable calculus. Although it may seem unrelated to programming, calculus is widely used in graphics, simulations, robotics, physics engines, and machine learning. Probability and statistics. Modern software often relies on uncertainty rather than certainty. This course introduces probability distributions, random variables, statistical inference, and hypothesis testing. These skills are fundamental for AI, data science, analytics, and predictive modeling. Software engineering. Writing code is only part of building software. Software engineering teaches how teams design, develop, test, document, and maintain large projects. You'll also learn version control, agile development, testing strategies, and software architecture used in professional environments. Database systems. Almost every application stores data somewhere. In this course, you'll learn relational databases, SQL, normalization, indexing, and transactions. Whether you're building a banking system or a social media app, databases are at the heart of modern software. Computer networks. Every email, video stream, and website depends on networking. Students learn about TCP/IP, routing, switching, network layers, and internet protocols. By the end of the course, you'll understand how information travels across the internet in milliseconds. Theory of computation. Can every problem be solved by a computer? Theory of computation explores automata, formal languages, computability, and computational complexity. Although highly theoretical, it defines the limits of what computers can and cannot accomplish. Programming languages. Programming languages aren't just tools, they're carefully designed systems. This course explores language syntax, semantics, compilers, interpreters, memory management, and different programming paradigms. You'll gain a deeper understanding of why languages behave the way they do. Systems programming. Systems programming brings you closer to the hardware. Using C in Unix or Linux, you'll learn about processes, system calls, memory allocation, and low-level programming. It's where software meets the operating system. Ethics in computing. Technology shapes society, making ethics more important than ever. This course examines privacy, cybersecurity, artificial intelligence, algorithmic bias, intellectual property, and professional responsibility. Great computer scientists build technology that is not only powerful but also responsible. Artificial intelligence. Artificial intelligence teaches computers to solve problems that normally require human intelligence. You'll explore search algorithms, knowledge representation, reasoning, planning, and intelligent agents. This course lays the groundwork for advanced topics like machine learning, robotics, and natural language processing. Machine learning. Machine learning enables computers to learn patterns from data instead of following fixed rules. You'll study supervised and unsupervised learning, decision trees, neural networks, and model evaluation. These techniques power recommendation systems and modern AI applications. Cryptography. How do online banking and messaging apps keep your information private? Cryptography explores encryption, digital signatures, public key systems, hash functions, and secure communication. It forms the backbone of cybersecurity and blockchain technologies. Human-computer interaction. Technology should be intuitive and easy to use. Human-computer interaction focuses on designing user-friendly interfaces through usability testing, accessibility, user research, and interaction design. Great software isn't just functional, it's enjoyable to use. Computer graphics. Computer graphics bring digital worlds to life. Students learn 2D and 3D rendering, animation, lighting, shading, geometric transformations, and graphics programming. These concepts are used in video games, movies, virtual reality, and scientific visualization. Distributed systems. Modern applications often run on thousands of computers simultaneously. Distributed systems teach cloud computing concepts such as replication, fault tolerance, synchronization, consensus algorithms, and scalability. Companies like Google, Amazon, and Netflix rely on these technologies every day. Cloud computing. Cloud computing explores how computing resources are delivered over the internet. Students learn virtualization, containers, microservices, serverless computing, and cloud platforms. This knowledge is essential for building scalable modern applications. Compiler design. Every programming language needs a translator. Compiler design explains lexical analysis, parsing, optimization, code generation, and runtime systems. You'll discover how source code becomes executable machine code. Parallel computing. How do supercomputers solve massive problems so quickly? Parallel computing teaches how multiple processors work together to perform tasks simultaneously. Students learn multithreading, GPU programming, synchronization, and performance optimization. Robotics. Robotics combines computer science with engineering to create intelligent machines. Topics include computer vision, motion planning, control systems, and autonomous navigation. Robotics is widely used in manufacturing, healthcare, and space exploration. Data mining. Data mining focuses on discovering useful patterns from massive datasets. Students explore clustering, classification, association rules, anomaly detection, and predictive analytics. These techniques help businesses make data-driven decisions. Mobile development. With billions of smartphone users worldwide, mobile development has become an essential skill. Students learn to build Android and iOS applications, create responsive interfaces, connect to cloud services, and optimize performance for mobile devices. Web development. Web development covers both front-end and back-end technologies. You'll work with HTML, CSS, JavaScript, databases, APIs, and web frameworks to create dynamic, interactive websites and web applications used by millions of people every day. Big data analytics. Organizations generate enormous amounts of information every second. Big data analytics introduces Hadoop, Spark, distributed storage, and large-scale data processing techniques that power recommendation systems, business intelligence, and scientific research. DevOps. DevOps bridges software development and IT operations. Students learn continuous integration, continuous deployment, automation, Docker, Kubernetes, monitoring, and infrastructure management to deliver software quickly and reliably. Capstone Project. The Capstone Project is where everything comes together. Students work individually or in teams to design, build, and present a complete software or research project. It's an opportunity to apply years of learning to solve real-world problems and demonstrate readiness for industry or graduate study. These courses form the core curriculum at the world's top-ranked computer science universities. Mastering them gives you the same foundation as students at leading institutions and prepares you for careers and beyond. Which course are you most excited to learn?